Hi everyone, we are continuing to talk about latent energy transfer. And to review, latent energy breaks the bonds in a solid to result in a transition of phase to a liquid. And the energy that broke the bonds in the H2O, ice, is now transferred to the bonds in the H2O water. We can also break the bonds in H2O water and create H2O water vapor. This latent energy transfer that breaks bonds builds up so that the gas is the most energetic state in water vapor, has an enormous amount of energy. Well, what does heat have to do with the move from solid to liquid to gas? Before we get into that, let's review that temperature is the average speed of molecules in an ice cube, or the average speed of molecules in a liter of water, or the average speed of water vapor in a room. And heat is the energy transfer that happens as a result of a difference in that substance. The energy transfer goes from higher energy, warmer substance to cooler energy, cooler molecules. It always transfers from more energy to lower energy in an attempt to make them balance in equilibrium. Equilibrium is a very important point in meteorology, and this is one of the first places that you find it when you talk about transfer of energy by heat. How does that impact what we're looking at for solids, liquids, and gases? Let's look at a really important graph that has an x-axis, a horizontal axis, and a y-axis. On this x-axis, we're starting here. This is like zero total heat, zero total energy transferred. And then we're adding heat and energy transfer. So this is our highest level of energy transfer. This is total heat on the x-axis. On the y-axis, there is Fahrenheit temperature, the average speed of molecules in H2O here. When we look at heat and its work with solids, liquids, and gases, heat warms solids, heat warms liquids, heat warms gases. We can move heat from the environment into the ice. This ice right here is at 0 degrees Fahrenheit. This ice right here is at about 15 degrees Fahrenheit. This ice here is right at the melting point at 32 degrees Fahrenheit. We can add kinetic energy, we can add warmth and heat into the ice to make it less cold. You know that when something is frozen solid, it's frozen around 0 degrees Fahrenheit. But if you had a very sunny day on pavement, it might warm that ice up to 32 degrees. And in fact, the pavement is moving the energy from the sun into the ice to warm it. Same thing, we can move heat into water to raise its temperature from 32 degrees cold water up to 212 degrees boiling water. That's all heat from the environment. In this case, you'd probably have heat warming from a kettle. The flame warms the kettle warms the water inside. So the environment is the kettle. You can also warm water vapor. Water vapor is very hot, but you can add more heat into it to create even higher temperatures for water vapor, well above the boiling point that produced the vapor in the first place. What does latent energy have to do with the move from solid to liquid to gas? Well, like we said, Latent energy breaks the bonds of the solid ice to form the liquid. And latent energy breaks the bonds of the water to create the vapor. So while kinetic energy changes the temperature, latent energy changes the phase. While the phase is changing, the temperature does not change. So in other words, when you are at 32 degrees, that ice becomes very slushy. And then after all of the slushiness has turned to water, then that water can increase in temperature. But while you are in the melting process, the temperature does not change. While you are in the boiling off process to make vapor, the temperature of the water in the kettle does not change. It stays at the boiling point until all of the water is boiled away. That is the latent energy that is breaking the bonds and not raising the temperature at the same time. You will find that heat can do one of two things. Either it can raise the temperature of the substance, or it can change the phase of the substance, but it can't do two things at once, one or the other. Where did the latent energy go? It broke the bonds and it got stored in the higher phase. In other words, the higher energy phase of water stored all of the energy that broke the bonds in the ice. The higher energy phase of the water in vapor stored all of the energy that broke all the bonds in the water. So let's review for a second. That latent energy originated in the environment. The pavement warmed the ice on top of it. When the pavement warmed the ice on top of it, the pavement lost thermal energy. It's now in the ice. It's raising the temperature of the ice. The pavement lost thermal energy and the pavement cooled. Now, when the energy came in to the kettle, well, the kettle warms the water. When the kettle is warming the water, it is actually taking thermal energy away from the kettle and putting it into the water. This process cools the kettle. That energy goes in to break the bonds in the water and produce water vapor, and it keeps the kettle cooler. Now you may say, that kettle is not cool. That kettle can cause severe burns if I touch it. And you're right, it can cause severe burns, but the kettle did not melt while it was boiling away the water. And in fact, when the kettle boils dry and there is no more water left to vaporize, that is when the metal on the kettle becomes dangerously hot and it can really damage the metal and weaken the metal. So while there is water in the kettle, the process of moving energy into the water means that there's less energy at the kettle and it keeps the kettle cooler. Melting is a cooling process for the pavement. Boiling is a cooling process for the kettle. Melting is cooling for the environment. Evaporation is cooling for the environment. Now, let me give you an example that you can understand. You step out of a shower and your skin is very hot from the hot water in the shower. You step out of the shower and the water on your skin takes in the hot skin heat from you. As the water takes in that hot skin heat and evaporates off, your skin feels cooler. The same thing happens with sweat. As you sweat, your sweat absorbs the heat from your skin. As it absorbs the heat from your skin, it takes the heat away from your skin and you feel cooler as your sweat is evaporating. So that evaporation is a cooling process. Just to keep in mind, water vapor, that evaporation is a cooling process, the resulting water vapor is invisible and still incredibly powerful because it has so much energy in it. That's one of the hardest things to understand in meteorology, that the phase of water that has the most energy is the phase of water that we cannot see. This is not water vapor. This is hot liquid water. So that the vapor in the room is invisible but has the most power. This is actually condensed vapor that is hot liquid water. Really important note to see. You don't see what's most powerful in the atmosphere. Just to keep in mind on what happens with the pavement when it cools, when it warms the ice. The same motion happens when we evaporate water from the ground, from the dew, and when we evaporate water from the oceans and from lakes. So the ground will absorb the sunlight and it will break the bonds of water that is on the ground or in the ocean, and those broken bonds will form water vapor. In doing so, it is taking the energy from the ground and from the ocean and putting it into the water vapor, keeping the ground and the ocean cooler because they lost thermal energy. So evaporation essentially keeps the surface of the ocean cooler, and it keeps the surface of the ground cooler. There's another way to look at this. We can go between one phase of solid to liquid to gas, or we can go directly from solid straight to gas. And you've seen that in dry ice. A block of dry ice goes straight to a cloud of white gas. And there's no liquid involved in that. Another process that you might be aware of is Vicks VapoRub. Maybe you've rubbed it on your throat. It's a solid, but it goes directly to a gas and it sublimates and makes your skin feel much cooler, especially when you're feverish, so that it takes the heat right from your skin and vaporizes it into a cool gas. This is called sublimation. It's not often seen in nature because you need to feel this or see it. And you feel it with the Vicks VapoRub, but you can't really feel water vapor. And it's invisible, so that we don't often know about sublimation in the atmosphere. At the same time, we see the effects of evaporation and potential energy when we have water vapor in the atmosphere. That water vapor, pound for pound, contains the energy of several atomic bombs. We're going to explore this more in the next video on how to release that energy. See you then.